lot of people ask me, what is quantum computing, and why do quantum computers pose such a threat to modern-day encryption? Now, classical computers use binary bits to store and manipulate data. These take on values of either 0 or 1, but quantum computers use quantum bits, or qubits, to store data, and these can take on a combination of 0 and 1 states. As a result, you're able to perform computations effectively in parallel on both the 0 and 1 state simultaneously. Now, this idea of superposition is incredibly powerful. There's also the idea of probabilistic measurement. You don't know what state your qubit is going to take, either a 0 or a 1, until you measure it. And then finally, the third crucial part about quantum computers is that you can have entangled pieces of information. So 2 qubits are entangled if they contain identical types of information. That's incredibly powerful for doing computations on a quantum computer that are simply impossible to do on a classical computer. Now, in 1994, Peter Shor, a professor here at MIT, wrote down an algorithm which, if ran on a quantum computer, can break factorization of large numbers. Basically, if I give you 2 prime numbers, ask you to multiply them together, that's a pretty easy thing to do. But the inverse, where if I give you a large number and ask you to give me its prime factors, you'd have a hard time doing that in a short amount of time. But with Shor's algorithm on a quantum computer, you can do it exponentially faster than on any classical computer. Now, a lot of modern-day encryption, like RSA, relies on the difficulty of factorizing large numbers. And quantum computers pose a significant threat to that very problem. So we need to be moving away from RSA, away from asymmetric encryption that relies on factorization, towards post-quantum cryptographic standards. Now, the National Institute of Standards and Technology, NIST, has come out with 3 approved post-quantum cryptographic standards, which are safe from future quantum attacks using Shor's algorithm. And so at Protegrity, we take a data-centric approach to security, and that means encrypting data at all points of risk. That includes the signatures and the data in transit that's asymmetrically encrypted, including the public and private keys that we use today. And so if we were to shift to post-quantum cryptography, we'd be safe against future quantum attacks using Shor's algorithm. At Protegrity, we're trying to figure out how we can do this in our systems and how we can help our customers do the same. So stay tuned for more on how we'll do that.